Chapter 0: The Origins and Philosophy of CSS. Every craft has a history. Every tool has an origin story that explains why it works the way it does. Before we write a single line of CSS, we need to understand the world that made it necessary, the broken, chaotic web of the 1990s, and the brilliant idea that fixed it. This chapter is the prologue, the foundation. We'll explore how CSS was born, how it evolved through war and compromise, and what that word cascading really means. Because if you master the cascade, you master the entire language. Section 0.1: The Problem Before CSS. Before CSS, the web looked like this. Imagine visiting a website that's nothing but a column of black text on a gray or white background. No columns, no custom fonts, no background images, just raw, unstyled content. In the very early days of the World Wide Web, around 1990 to 1993, that was the entire experience. The web was built as a platform for sharing scientific documents, not for design. HTML, the language for structuring content, had only a handful of tags, headings, paragraphs, lists, links, and absolutely no way to control colors, spacing, or layout. If you wanted to make something look even slightly different, you were out of luck. This is the story of the deep frustration that led to the invention of CSS. Then came the desperate hacks. As the web grew, people wanted their pages to stand out. Browser vendors added new HTML attributes to let designers control appearance directly. You could slap a color attribute onto the body tag to change the background color of an entire page. You could wrap text in font tags with a face to choose a typeface, a size from 1 to 7, and a color using a name or hex code. At first, it felt like freedom, but the code got messy fast. To make a heading bold, red, and centered, you'd write something like center B font color equals red welcome /font /B /center. Every visual decision was baked into the HTML itself. There was no separation between content and presentation. And that was only the beginning of the nightmare. To achieve anything resembling a modern layout, designers turned to the only tool that offered any structural control: the HTML table element. Tables were never meant for page layout. They were created to display tabular data. But by the mid-1990s, slicing up a design into a grid of table cells became the universal trick. Designers would nest tables inside tables, sometimes 5 or 6 levels deep. They'd insert transparent 1-pixel GIFs, called spacer GIFs, stretched to specific widths to push cells apart. The result was a house of cards. A page that looked like a neat magazine layout in the browser was a terrifying maze of unreadable markup behind the scenes. Updating a single column meant digging through endless TD tags, praying you didn't break the entire structure. And if a user's screen was slightly smaller, the whole layout could shatter. But the true horror of this approach hit when you needed to make a global change. Say you ran a site with 100 pages, all using the same deep blue color for headings and background accents. Then your boss decides the brand color is now green. In a sane world, you'd change one line of code. But in the era of presentational HTML, that color was scattered across every single page. Inside font tags, inside TD background attributes, inside color on table cells. There was no central place to update it. You'd have to open every file, find every instance of that color, and manually replace it. Some files might use the hex code 000080, others the color name navy, others might even use dark blue. A simple rebrand could take days or weeks, and you were almost guaranteed to miss something. Maintenance was a nightmare. At the heart of this mess was a violation of a fundamental software principle: separation of concerns. HTML was supposed to describe the structure and meaning of content. This is a heading, this is a paragraph, this is a navigation menu. But when you stuffed it full of font tags and layout tables, you mixed that pure structural meaning with visual instructions. The same content couldn't be easily repurposed for different devices like mobile phones or screen readers because the presentation was hardwired into the markup. A blind user's screen reader would stumble over non-semantic table cells used for spacing. A printer-friendly version was a whole separate file. The web community desperately needed a way to keep the content clean and the styling separate. That desire became the driving force behind CSS. By 1994, the situation was unsustainable. Web designers were exhausted by the fight with HTML to force it into a design tool. The web was growing explosively, and the tools for visual expression were utterly broken. There had to be a better way, a dedicated language that could describe the presentation of a document without polluting its structure. That language would need to let you define styles once in one place and have them apply consistently across an entire site. It would need to handle the complexities of layout, fonts, colors, and spacing elegantly. And above all, it would need to let style sheets flow together, combining author, user, and browser preferences in a predictable way. The stage was set for the birth of cascading style sheets. Section 0.2. The birth of CSS. To understand how CSS was born, we have to travel back to the early 1990s. The World Wide Web was still an experiment. Tim Berners-Lee had created it at CERN, the European Particle Physics Laboratory, as a way for researchers to share documents across different computers. The web was revolutionary, but it was also painfully plain. Every page was black text on a gray background, broken up by blue underlined links. There were no fonts, no colors, no layouts. The web's creator, Tim Berners-Lee, had deliberately kept HTML simple, focused entirely on the structure of information. But as the web started to escape the lab and reach a wider audience, a new demand was growing. People wanted it to look good. And that's where our story really begins. The hero of this story is a Norwegian computer scientist named Håkon Wilhelm Lie. He arrived at CERN in 1994, fresh from MIT's Media Lab, where he had worked with the brilliant interface researcher Walter Bender. Håkon was fascinated by electronic publishing. He had seen how desktop publishing software let you apply consistent styles across entire documents, and he knew the web needed something similar. At the time, the web was in a tug-of-war. The designers pushing for visual control were resorting to font tags and table hacks, while the purists wanted to keep HTML clean and semantic. Håkon saw a third way. Instead of polluting HTML with presentation, why not create a separate language that would handle all the styling? In October 1994, he published a proposal titled Cascading HTML Style Sheets, the very first sketch of what would become CSS. But Håkon didn't invent the idea of style sheets out of thin air. The concept was already well established in the world of desktop publishing and document markup. Programs like PageMaker and Ventura Publisher allowed users to define style sheets, collections of formatting rules with names like body text or heading 1, and apply them consistently across a publication. In the standards world, there was SGML, the standard generalized markup language, which had a mechanism called DSSSL to transform and style documents. Even HTML's own parent language, SGML, separated structure from presentation. The web, however, had none of that. Håkon's insight was to bring the same separation to the chaotic world of the web browser. A style sheet language would let authors define how a document should look without changing the document itself. It was a return to a clean separation of concerns. The core idea of CSS was brilliantly simple. An HTML document would contain only content and its semantic structure: headings, paragraphs, lists, links. All the visual decisions, colors, fonts, margins, alignment, would live in a separate style sheet, a .css file linked from the HTML. The browser would read both and combine them to render the page. Even the name was carefully chosen: Cascading Style Sheets. The cascade was the mechanism that allowed multiple style sources, the browser's own defaults, the user's personal preferences, and the author's design to flow together in a controlled waterfall of priority. It gave power to everyone. Designers got the visual control they wanted, users could override styles if needed, and the HTML remained clean and accessible. This was the breakthrough. The proposal didn't stay a personal project for long. The World Wide Web Consortium, the W3C, founded by Tim Berners-Lee in 1994, quickly recognized the need for a styling standard. A CSS working group was formed, and Håkon Wilhelm Lie became its first chair. He was soon joined by Bert Bos, a Dutch researcher who had independently developed a browser called Argo with its own style sheet system. Together, they refined the proposal, debated syntax, and navigated the stormy politics of browser vendors who each had their own ideas. By the end of 1996, the W3C published the first official CSS specification, CSS Level 1. It covered fonts, colors, text properties, margins, borders, and basic positioning. It was a modest but crucial first step, a real implementable standard. CSS wasn't the only contender. The SGML community had already developed a powerful but terrifyingly complex styling language called DSSSL, the Document Style Semantics and Specification Language. It was a full programming language based on scheme, complete with loops and functions. While incredibly powerful, it was far too complex for the everyday web designer. Another proposal called PSL, the Presentation Style Language, was slightly simpler but still lacked the elegance that the web needed. CSS won because it was designed for the web from the ground up. The syntax was human-readable, declarative, and forgiving. You didn't need a computer science degree to write H1 color blue. It was lightweight, easy to implement in browsers, and, crucially, it embraced the network's unpredictability with the cascade. The simpler solution won. The birth of CSS was a quiet revolution. It didn't change the web overnight. Early browser support was buggy and inconsistent, a challenge we'll explore in the next section. But the blueprint was perfect. Hakan Lai and his collaborators had planted a seed. The idea that content and presentation could be cleanly separated, that style sheets could cascade, and that the web could be both functional and beautiful. From that first proposal in a hallway at CERN, CSS would grow to become an indispensable pillar of the web, alongside HTML and JavaScript. And the journey had only just begun. Plain Script, Section 0.3. The Evolution CSS 1, CSS 2, and CSS 2.1. When CSS Level 1 became an official W3C recommendation in December 1996, it was a moment of genuine hope. Finally, the web had a standardized way to describe fonts, colors, text alignment, margins, borders, and even basic floating. The specification was clean, concise, and forward-looking. Designers could write a single style sheet and, in theory, have it work across any CSS-aware browser. But theory and reality are two very different things. As the first browsers attempted to implement CSS1, it quickly became clear that the road to consistent styling would be long and painful. Browsers added CSS support in a piecemeal, buggy, and often wildly incompatible way. The dream of write once, render anywhere was about to crash headfirst into the chaos of the browser wars. The late 1990s were the height of the so-called browser wars. Netscape Navigator and Microsoft Internet Explorer were locked in a fierce battle for market dominance. Both companies raced to add new features, but standards compliance was often an afterthought. CSS support became a casualty of this war. Internet Explorer 3, released in 1996, had a partial, buggy implementation. Netscape 4, released in 1997, was even worse. It often required a page reload to reapply styles after a window resize. The box model was a particular disaster. IE calculated an element's width differently, including padding and borders in the specified width, while Netscape followed the spec. Developers had to write separate style sheets, use JavaScript to detect browsers, or simply abandon CSS for the safety of table layouts. It was the era of best viewed in X badges, and the web was fracturing. In 1998, just 2 years after CSS1, the W3C published CSS Level 2. It was an enormous leap forward. CSS2 introduced absolute, relative, and fixed positioning. It added z-index to control stacking order. It defined media types so you could write one style sheet for screens and another for printers. It brought system colors, table layout properties, generated content with before and after, and much more. In theory, it was everything a designer could want. In practice, it was a tease. No browser fully implemented CSS2. Each vendor cherry-picked the features they liked and ignored the rest. Developers were forced to create elaborate hacks, the Holly hack to target IE, the underscore hack for older browsers, conditional comments, just to deliver a consistent experience. CSS had grown powerful, but the gap between specification and reality had never been wider. By the early 2000s, the W3C realized that CSS2 was too ambitious and too loosely specified to be fully interoperable. Instead of pushing forward to CSS3, they made a bold decision. They would go back and create CSS 2.1. This would not be a new feature set, but a cleaned-up version of CSS 2, removing everything that was never properly implemented, fixing errors, and clarifying ambiguities until every rule was testable and could be implemented consistently. The process was painstaking, took nearly a decade. Drafts were published, reviewed, and rejected. Features were cut if no two browsers implemented them the same way. The infamous candidate recommendation phase required an implementation report proving that every feature could pass test cases in at least 2 shipping browsers. Finally, in June 2011, 13 years after CSS2, CSS 2.1 became a full W3C recommendation. For the first time, the web had a stable, reliable baseline for CSS. It was the bedrock everything else would be built upon. A crucial force in this march toward compatibility was the acid tests. Created by the Web Standards Project, a grassroots group of developers fed up with broken browsers, the acid tests were designed to expose non-standard behavior. Acid 1, released in 1998, tested basic CSS1 rendering. Acid 2, in 2005, demanded pixel-perfect implementation of a small but devilish set of CSS 2.1 features, including absolute positioning, generated content, and the infamous has-layout bug in Internet Explorer. Browsers that failed displayed a grotesque mess. Those that passed showed a cheerful yellow smiley face with a green background. The tests became a public scoreboard. Browsers rushed to pass Acid 2. Internet Explorer 8 was the last to do so, after a complete rewrite of its rendering engine. Acid 3 followed in 2008, pushing even further. These tests weren't just about scores. They shamed browser vendors into action and gave developers a clear, objective measure of progress. The acid tests helped turn the browser wars from a destructive battle into a race toward standards. The story of CSS1, CSS2, and the long march to CSS 2.1 is not just a history lesson. It's the reason CSS works today. By the time CSS 2.1 was finished, the browser landscape had transformed. Internet Explorer SIX's dominance had been challenged by Firefox, Safari, and eventually Chrome. All of them were built with a commitment to standards that would have been unthinkable a decade earlier. Developers could finally write a style sheet and trust it would work across browsers. That trust, hard-won over years of pain, is the foundation on which the modern CSS renaissance was built. With a solid baseline in place, the stage was set for something new. A modular, ever-evolving CSS, no longer tied to version numbers like 3, 4, or 5, but living and growing alongside the web itself. Section 0.4, CSS3 and the Living Standard. With CSS 2.1 finally providing a stable foundation, the W3C faced a critical question. What next? The old model of releasing one massive, monolithic specification had proven nearly impossible to get right. It took 13 years to fix CSS2, and the web couldn't afford another decade of stagnation. The answer was radical and brilliant. Instead of one giant CSS3 specification, they would break CSS into independent modules. Each module would cover a specific area: selectors, color, backgrounds, fonts, animations, layout, and each would evolve at its own pace. This modular approach was a fundamental shift in how CSS was designed, developed, and shipped. It meant that a breakthrough in animations didn't have to wait for the grid layout module to be finished. The web could move faster, and it did. Under this new system, each CSS module has its own version number, completely independent of the others. There is the selectors module, the color module, the backgrounds and borders module, and dozens more. Each one advances through its own levels. So you might have selectors level 3 as a finished recommendation, while selectors level 4 is still a working draft. The color module could be at level 4, while the grid layout module is at level 1. This is why the term CSS3 is technically a misnomer. There is no single specification called CSS3. Instead, CSS3 became a loose, collective nickname for all the new capabilities that arrived after CSS 2.1. It's a marketing term, a convenient label for a whole ecosystem of specifications that are perpetually in motion. Today, we don't talk about CSS4 or CSS5. We talk about specific module levels and browser support. This modular architecture also changed how the specifications themselves are maintained. Instead of aiming for a single monumental version release every few years, the CSS working group adopted a living standard model. Each module is continuously updated with new features, clarifications, and fixes. When a feature is mature and has multiple interoperable implementations, it can graduate to recommendation status. But the module itself never closes. It just moves on to the next level with more features. Think of it like an orchard, not a factory. Each tree grows at its own rate, bearing fruit when it's ready. Some modules, like selectors, are on level 5 already. Others, like the newly proposed toggle or functions modules, are just seeds. This evergreen approach keeps CSS vibrant and responsive to the needs of developers and users. For browser vendors, the modular living standard changed everything. In the old days, a browser would try to implement an entire CSS version all at once, often falling short. Now, vendors can pick and choose which module features to work on. They implement new capabilities behind feature flags, experimental toggles that developers and early adopters can test. This allows real-world feedback before a feature is finalized. When the feature is stable and the specification is solid, the vendor ships it by default to all users. This implement, test, ship cycle repeated across different browsers is what makes modern CSS so reliable. It also means that today, we often see new CSS features arrive in browsers within months of being proposed, not years or decades. The modular system created a virtuous cycle. Faster implementation feeds better specifications, which in turn encourages faster implementation. Let's demystify the terminology you'll see on CSS specification pages. An editor's draft is the bleeding edge version, maintained by the specifications editor. It changes daily and isn't stable. A working draft is the first official stage published by the working group, meaning we think this is worth discussing, but it's still very fluid. A candidate recommendation is a major milestone. The specification is stable, and the working group is actively gathering implementation experience to prove that the features can work consistently across at least 2 browsers. This phase can take years and often sends the spec back to working draft if problems are found. Finally, a proposed recommendation is a final check before the document becomes an official W3C recommendation, a standard. But even recommendations can be updated with errata or replaced by a higher level. The whole system is designed for iteration, not perfection. The modular, living standard approach has unleashed a golden age for CSS. Features that once seemed like science fiction, flexible box alignment, grid layouts, custom properties, container queries, scroll-driven animations are now part of our everyday toolkit. They arrived not as a single big bang, but as a steady stream of innovations, each module maturing at its own rhythm. The old pain of waiting for a monolithic CSS to solve all problems is gone. Instead, we have a CSS that grows with us, that adapts to new devices and new design challenges as they emerge. This is the modern reality. CSS is not a finished product with a version number. It is a living, breathing language, and you are part of its ongoing story every time you write a style sheet. The next chapter? How CSS became not just a styling language, but one of the 3 essential pillars of the web. Section 0.5. CSS as a pillar of the web. The modern web stands on 3 pillars: HTML, CSS, and JavaScript. Each has a distinct and irreplaceable role. HTML provides the structure and meaning, the skeleton of content. JavaScript provides the behavior and interactivity, the muscles and nerves that respond to user actions. But CSS is the skin, the clothes, the visual identity. It transforms a bare skeleton into an experience that can be elegant, playful, professional, or immersive. Without CSS, the web would be nothing but a stream of black text on white backgrounds. Without CSS, there are no layouts, no colors, no rhythm, no visual hierarchy. CSS is not just decoration. It is the language of design on the web, and its role has only grown more essential as the web has matured. To see how, let's look at what CSS makes possible. First and foremost, CSS is the engine of responsive design. The explosion of mobile devices in the late 2000s could have shattered the web. Suddenly, a site designed for a 1024-pixel-wide desktop monitor had to work on a 320-pixel-wide phone screen. The solution was not separate websites for each device, but flexible, responsive layouts driven by CSS. Media queries allowed styles to adapt based on screen size, resolution, and even user preferences. Flexbox and Grid gave us layout tools that could reflow content without hacks. Modern CSS functions like clamp and viewport units allow typography and spacing to scale fluidly. Today, a single HTML document can deliver an optimal reading experience on a watch, a phone, a tablet, and an ultra-wide monitor, all thanks to CSS. Responsive design is not a feature of CSS. Responsive design is CSS. Beyond layout, CSS is the technology that enables theming and design consistency at scale. With custom properties, CSS variables, you can define a palette of colors, spacing scales, and typographic styles once, and reuse them everywhere. Changing a single variable like brand color instantly updates every button, heading, and border across hundreds of components. This is the foundation of design systems and component libraries. Combine custom properties with media queries for prefers color scheme, and you get automatic dark mode support. Combine them with JavaScript toggles, and users can personalize their experience. This wasn't possible in the font tag era. It required a style sheet language that understood variables, cascading, and dynamic updates. CSS custom properties, now a core feature, make entire applications themable with a few lines of code. CSS plays a crucial role in web accessibility. When we separate presentation from structure, we allow assistive technologies like screen readers to work with clean, semantic HTML. A visually stunning navigation menu built from semantic NAV and UL elements is still navigable by keyboard and announced correctly to blind users. CSS can enhance accessibility further. Focus visible styles make interactive elements clearly visible to keyboard users without cluttering the mouse experience. Prefers reduced motion media queries let you disable animations for users with vestibular disorders. High contrast mode queries ensure readability. Even simple choices like using relative units for font sizes respect the user's browser preferences. Good CSS, written with accessibility in mind, makes the web usable for everyone. Bad CSS, or no CSS at all, can create barriers. The separation of content and presentation is not just an architectural ideal. It's a foundation of an inclusive web. As CSS itself grew more powerful, the way we organize and write it matured as well. The early days of CSS were marked by unmaintainable chaos, global name collisions, ever-increasing specificity battles, and style sheets that nobody dared to edit. In response, the community invented methodologies. BM gave us strict naming conventions. ITCSS and SMACSS taught us how to layer styles from generic to specific. Utility-first frameworks like Tailwind CSS pushed the idea that single-purpose classes are more composable and predictable than deeply nested, content-specific selectors. CSS modules and CSS in JS libraries brought component scope styles into JavaScript frameworks. But at the heart of all these approaches is the same lesson. CSS is a powerful language that rewards structure, discipline, and a deep understanding of its core mechanisms, the cascade, specificity, and inheritance. We are living through a CSS renaissance. Features that would have required JavaScript libraries a decade ago are now native to the language. Grid and Flexbox solved layout problems that tortured a generation of web developers. Container queries finally gave us true component-based responsive design. The has selector, long known as the parent selector, unlocked possibilities that change how we think about styling. Scroll-driven animations and view transitions bring cinema-quality motion to the web with zero JavaScript frameworks. Even in the age of React, Vue, and Svelte, where JavaScript builds the user interface, the actual visual output is still rendered by CSS. Understanding how to wield these modern CSS features is what separates a junior developer who copies and pastes from a professional who crafts experiences. In a web development world increasingly dominated by JavaScript frameworks and abstractions, it's easy to think of CSS as an afterthought, something a component library handles for you. But the truth is, CSS is a deep, nuanced language, and when you truly understand it, you become dramatically more effective. You stop fighting the cascade and start harnessing it. You build layouts that adapt gracefully instead of breaking. You write less code that does more. You can debug visual issues that others find baffling. Learning CSS deeply is one of the highest leverage investments you can make as a web developer. It's the language that gives form to the web, and mastering it puts the full power of visual design at your fingertips. And it all starts with understanding the single most important word in cascading style sheets, the cascade itself. Section 0.6. Understanding cascading. Why it's called cascading style sheets why is it called cascading style sheets? The word is not a whimsical choice or a marketing term. It describes the very heart of how CSS works. A precise, multi-step algorithm that determines which styles actually get applied to an element when multiple rules compete. Think of a waterfall. Multiple streams of water flow down, merging, overriding, and blending, until they form a single pool at the bottom. In CSS, those streams are the different style sources, the browser's defaults, your own style sheet, maybe even the user's preferences, all flowing together. The cascade is the set of rules that governs this merging. It answers one fundamental question. When two or more declarations conflict on the same element, which one wins? Understanding the cascade is the single most important thing you can learn in CSS. In the cascade, style rules come from three main origins. First, the user agent style sheet, that's the browser's own built-in CSS. It gives headings their default size and boldness, adds margins to paragraphs, and turns links blue. Second, the user style sheet, the personal preferences a user can set, like a minimum font size or a high-contrast color scheme. And third, the author style sheet, that's you, the web designer or developer, linking your own CSS files. All three of these sources provide declarations for the same elements. The cascade takes these competing rules and sorts them into a precise order of importance. Without it, your beautiful design might be overwritten by browser defaults, or a user's accessibility needs could be ignored. The cascade balances the power between the browser, the user, and the author. The cascade algorithm itself follows a strict four-step sorting process. When multiple declarations target the same element and property, the browser runs them through this funnel. Step 1. Origin and importance. Declarations marked. Important by the author override normal author declarations. User. Important declarations override even those, ensuring users can always enforce their accessibility needs. Step 2. Cascade layers. The @layer rule lets you group your styles into explicit priority tiers so you can, for example, make your base framework styles always lose to your custom overrides, regardless of specificity. Step 3. Specificity. If the origin and layer are tied, the more specific selector wins. An ID beats a class beats an element name. Step 4. Source order. If everything else is perfectly equal, the rule that appears later in the style sheet wins. This four-step cascade is deterministic. It's not magic, it's math. Let's zoom in on specificity, the most misunderstood part of the cascade. Specificity is calculated as a three-part value: ID selectors, class/attribute/pseudo-class selectors, and type/pseudo-element selectors. Think of it as a three-digit number where IDs count in the hundreds, classes in the tens, and elements in the ones. So an element selector like h1 has specificity 001. A class like .headline is 010, beating h1. An ID like main title is 100, beating both. If you combine them, say, h1.headline main title, you get 111. But remember, specificity is only one step of the cascade. And Important declaration at a low specificity can still override a higher specificity rule, because importance is checked first. This is why understanding the entire funnel is crucial. Relying solely on specificity leads to wars of ever-increasing selector weights, and that way lies madness. There's a companion concept that works alongside the cascade: inheritance. Some CSS properties, when set on a parent, automatically pass their value down to their children. For example, if you set font family on the body, every heading, paragraph, and link inside will inherit that font, unless you override it. This is why you can style an entire page's typography with a single rule. But not all properties inherit. Things like margin, padding, border, background, and width do not. You wouldn't want every span inside a div to have a border. The distinction is logical. Text and list style properties generally inherit. Box model and layout properties generally don't. Inheritance reduces repetition and keeps your style sheets dry. It's the quiet partner of the cascade. The cascade resolves conflicts, and inheritance fills in the gaps where you haven't declared anything at all. So the cascade is the grand orchestrator. It takes all the competing style rules from all their different sources, weighs their importance, respects their layers, calculates their specificity, and finally falls back on source order. Then, for any property that still hasn't been set on an element, inheritance steps in to provide a sensible default from the parent. Together, the cascade and inheritance are what make CSS predictable, powerful, and maintainable. They are not bugs to be fought. They are features to be harnessed. When you understand the cascade, you stop using important as a hammer and start writing styles that flow naturally. You debug layout problems by tracing the cascade, not by guessing. Every topic in this course, selectors, the box model, flexbox, grid, animations, will be built upon this foundation. You now know the story of CSS, where it came from, how it evolved, and why cascading is the most important word in its name. Let's start writing some styles.